Hello guys, welcome back. So here we have another question on communication systems from GATE EC 2024. Let x of t equal to a cos 2 pi f naught t plus theta be a random process where amplitude a and phase theta are independent of each other and are uniformly distributed in the intervals minus 2 comma 2 and 0 comma 2 pi respectively. So this you can think of a cosine signal whose amplitude and phase are going to be random. Okay, and this x of t is fed to an 8-bit uniform mid-rise type quantizer. Given that the autocorrelation of x of t is Rx of tau equal to 2 by 3 cos 2 pi f naught tau, the signal to quantization noise ratio in dB rounded off to 2 decimal places at the output of the quantizer is dash. So we have the noise x of t. This is passed through a quantizer. And then you have your output signal. Let's call it some y of t. So this is going to be quantized and also it might be sampled. So it might be some y of n. Okay. And we need to find the signal to quantization noise ratio. So SQNR of this quantizer. And for this signal x of t. So what is SNR? SNR is signal to noise ratio. Signal to noise ratio. So this is nothing but your power of signal to power of noise. You can also call total power of signal to total power of noise. So for SQNR, we're actually dealing with the quantization noise. So what is this quantization noise? So if you observe, our input is some, let's say some analog waveform, which just have some sinusoidal variation. Now if you pass it through a quantizer, it's going to have discrete steps, right? It's going to have some discrete steps like this. And if you take the error of it, and your error waveform might be something like this. And this is what is called as your quantization noise. And this will have some distribution E of t, and from this distribution we can actually calculate the total power of this quantization noise. Similarly, in this case our input is also having some distribution, so from this distribution also we can calculate the total power of our input signal. And there is also another thing mentioned, which is nothing but 8-bit uniform mid-rise type quantizer. So our quantizer is 8-bit. And what is this mid-rise type? So there is also another called as the mid-thread type. So mid-rise type is, let's say we have range from some minus V to V. Our quantization will look something like this. In the middle actually we have the rise. Okay. Similarly, in the mid-thread type, here we have the flat thing in the middle. And it has 8-bit levels. 8-bit means 2 power 8 levels. So this is going to be even number, right? So here if you see 0 is not included. So it is like some plus delta by 2 minus delta by 2, or some we can call this level as plus 1 minus 1, something like that, right? So it is going to have symmetric levels. So if it is plus n here it will be minus n. On the other hand, here it includes the level 0. So once you exclude 0 from here, it becomes a odd number. So odd numbers you cannot evenly divide. So one side it will have some n and other side it will have n minus 1 levels. So it is going to be asymmetric. So anyway, now we are dealing with this one. And if you notice, our analog signal is going to be like this, right? So what will be our error signal? Our error signal is going to be, so here if you see, it is going to have plus and then it reduces, it becomes negative, again it rises. So it is going to have something like this. And this distribution we can assume that it is going to be uniform. And what are the minimum and maximum values from here? So this is 0, and if my step size is delta, it is going to vary from minus delta by 2 to plus delta by 2. So this is also minus delta by 2 to plus delta by 2. Okay. So this is my distribution of my error function. You can call it some error of x versus x. So how do I find this delta? So this delta is nothing but my step size. So what is the total range here? It is minus v to v. In this case, what is the total range? It can take, it is minus 2 to 2. So the total range is 4, and this divided by the number of steps. Number of steps is, here it is 8-bit level. So the number of steps will be 2 power 8 minus 1. Because one of them will be the base, right? So from there you are calculating how many steps. So it will be 2 power 8 minus 1. So 2 power 8 is 256. So this is 4 by 255. So this is my delta, or the step size. So now this distribution we have. So from here, how do we get our total power? So if you remember from our previous discussions of previous questions, the total power is nothing but your integral of your power spectral density, right, over the entire frequency range. And this was nothing but your autocorrelation function. So R error of 0, right? And this was nothing but your variance sigma square. And this was nothing but your variance sigma square when the mean is 0. Here also the mean is 0, right? So we just need to find the variance of this. So variance is nothing but expectation of x square. So expectation of error square is nothing but integral minus delta by 2 to delta by 2. And what will be this? This will be 1 by delta, right? So we need to take 1 by delta square. Sorry, this is the probability, which is 1 by delta, and we have some x square into dx. And we are integrating dx from minus delta by 2 to delta by 2. So this is equal to 1 by delta x cube by 3 minus delta by 2 to delta by 2. So this is equal to 1 by delta into x cube is delta cube by 8 into 3 and into 2. So which is equal to delta square by 12. So you can also remember this. For a uniform distribution, the total noise, quantization noise, is equal to delta square by 12. So delta we already know. So I'll call it quantization noise power is equal to delta is 4 square by 255 square into 12. So this is for my noise. What about the signal? Signal power is equal to, again same, signal also has a distribution, right? So it will be given by the variance, which will be nothing but the autocorrelation function Rx of 0. And here they have already given the autocorrelation function. So if they haven't given the autocorrelation function, you have to actually take this x of t, multiply with it with x of t plus tau, and do the integration to find your autocorrelation function. And you will be integrating over this ranges for a and theta. So but here they have directly given, so we can directly use it. So Rx of 0 will be 2 by 3 cos 2 pi f naught into 0. So Rx is equal to 2 by 3 cos of 2 pi f naught tau. Rx of 0 is just 2 by 3. So signal power is equal to 2 by 3. Total signal power is 2 by 3. So now what is my SQNR? This 2 by 3, or the total signal power, divided by quantization noise power. Total quantization noise power. So this is equal to 2 by 3 divided by 4 square by 255 square into 12, which is 2 by 3 into 255 square into 12 by 4 square. So this you can find from the calculator. So this comes to 32,512.5. So now they are asking in dB and round off to 2 decimal places. So since this is in power terms, this is watt by watt, we need to actually take 10 log of this, not 20 log. 20 log comes only when it is in volt by volt or ampere by ampere. Since watt is equivalent to whole square by whole square, right? That factor of 2 goes away. Okay, so it is 10 log 32,512.5, and using calculator this comes to be 45.12 dB. So this is the answer. Although it may have seemed very long and everything, so few important things to notice. You need to remember this, and this is very easy to remember. And also from the derivation also, you know, once or twice if you derive, you will be able to easily remember this. So once you have this delta, you can calculate easily. So this is your first step. And second step, and you already found your quantization noise power. And your third step is just directly finding your signal power, and fourth step is dividing them, fifth step is taking log. That's all. It is very simple. Okay, so at the top level you just need to understand what is happening, and you need to have very good knowledge of all the terms used here. Okay, so the answer is 45.12.